Hello everyone, welcome to my channel. We are on to the second lecture of thermodynamics, class 11. In the previous video, I have discussed about the various terms. That is basically the introduction of thermodynamics. In this video, we will be talking about heat capacity, specific heat capacities, their formulas and where we can apply them. Right. Now first let us understand what is heat. Heat is defined as form of transfer of energy when there is temperature difference. It is actually a form of transfer of energy from where? From one system to the another, or you can say from system to surrounding, or from surrounding to system. So it's form of transfer of energy between two objects also you can have, between two systems we can have when there is a temperature difference. If suppose you take two systems which are having same temperature, if they are having same temperature, the transfer of energy cannot be in the form of heat. Okay, if it has to be transfer of energy in the form of heat, that is only possible if the two are at some temperature differences there between the two, right? And the symbol of this heat we write down as Q. The unit for this is joule. We also write sometimes calories, where you have a relation like 1 calorie is equal to 4.2 joules. Okay. Now suppose we talk in terms of a system. You have some system and the system is giving out heat. If it is giving out heat, we will write down heat given by the system. Heat given by the system, we always write with negative sign, that is minus Q you write, minus Q. Heat given by the system is minus, that is exothermic. This is the thing which we are taking in chemistry. In chemistry we talk about system losing heat. Or if we are talking about heat taken by the system, heat taken by the system. System has taken the heat. If it has taken the heat, it is represented with plus sign. This concept you have to understand, plus and minus, right? If it is giving out, it is minus. If it is taking heat, then it is positive. It's endothermic, this is exothermic. Clear? So that part is clear. Like if a system is losing heat, if it is giving out heat, then energy of the system lowers. When it is absorbing heat, the heat is taken by the system, then its energy is increasing, right? Now we'll move on to the next term, heat capacity. Heat capacity. Now what is heat capacity? Heat capacity of a system is defined as the amount of heat required to raise the temperature of system by 1 degree Celsius. 1 degree Celsius. Whatever system you have taken, that system's temperature, if we are increasing by 1 degree Celsius, what is the amount of the heat required? That is called as heat capacity. We will represent this heat capacity by the symbol C. That is written as, suppose Q is the amount of the heat required by the temperature difference. Okay, by temperature difference. That is called as heat capacity. Heat capacity is Q by delta T. Obviously, if we are increasing it by 1 degree, that delta T will be 1. So whatever is the temperature difference, say from T1 temperature it has gone to T2. So T2 minus T1, that will be delta T. And Q is the amount of the heat required. Right. So if we are writing the unit of this heat capacity, so it will be, unit will be joule for this per Kelvin. Joule per Kelvin, that is the unit of heat capacity. So this is the second term we have done. We have done heat, another we have done is heat capacity. Now we'll move on to the next term, that is specific heat capacity. Specific heat capacity. Now what is this specific heat capacity? Symbol for this we can write down C, small c I'm writing, small c. Right, so we can define this specific heat capacity as amount of heat required, amount of the heat required to raise the temperature of 1 gram of substance, 1 gram of substance by 1 degree Celsius. We specify the amount here. You have some substance which is 1 gram. 1 gram substance, if we want to increase its temperature by 1 degree Celsius, 1 gram substance by 1 degree Celsius, how much is the heat required? That is called as the specific heat capacity. Right, so we can write the formula as C. C is equal to Q by M delta T. M delta T. Right, where you are taking this as the mass, which will be converted into 1 gram, because for 1 gram we are calculating for 1 gram 1 degree rise, what is the heat required? That will be called as the specific heat capacity. Okay, so when we are discussing questions, then this will be clear. For if any other mass is given, for any other mass, what is the heat capacity, specific heat capacity, we can calculate using this formula. Now, what unit we will write down for the specific heat capacity? Unit will be for this joule, for this per gram. For 1 gram we are saying temperature difference, we can write down degree Celsius, per degree Celsius, or at times per Kelvin also. So you can have this joule per gram per Kelvin. So this is the unit of specific heat capacity. Clear? Yeah, now another interesting thing here. Suppose we consider isothermal, or we are talking about adiabatic process. Isothermal process or adiabatic process. What is isothermal process? We know the temperature remains constant. Adiabatic process, where the heat remains constant. If we are measuring the specific heat capacity for isothermal process or for the adiabatic process, what will be the specific heat capacity? We can just put in this formula. Specific heat capacity, this is equal to Q by M delta T. Now this is constant, we are saying. At constant temperature we are measuring, means this term is 0. When this term is 0, what will be the specific heat capacity? It tends to infinity. Specific heat capacity for isothermal process is infinity. If we are talking about adiabatic process, means Q is constant, Q is not changing, right? So then you will have this is equal to Q by this M delta T. So this becomes 0. So this becomes 0, means it will be 0 then. Clear? So at constant heat you are measuring that adiabatic process. So specific heat capacity will be 0. The specific heat capacity for a gas can vary between 0 to infinity. Yeah, at times it's given like this. Say we measure the specific heat capacity at constant pressure. If we measure whatever thing is given, amount of the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius at constant pressure, then we will represent this with Cp. So Cp will be amount of the heat required to raise the temperature of 1 gram by 1 degree at constant pressure. We are writing as Qp. M delta P. So likewise, if it is at constant volume, we will write down this as Cv is equal to heat absorbed at constant volume by M delta T. Okay, so this is specific heat capacity at constant pressure. This is specific heat capacity at constant volume. This is small letter c. This is not that capital C. Okay, so that we will be talking about after this. Now moving on to another term, that is molar heat capacity. Molar heat capacity we write with the capital letter C, and we define this as amount of heat required to raise the temperature of 1 mole of substance. Instead of 1 gram, now we say 1 mole of substance by 1 degree Celsius. 1 mole of substance. So whatever formula we wrote earlier, now we will write down as capital C is equal to Q by M delta T we wrote. Now we will write down number of moles into delta T. Okay, we will write down as Q N delta T. Same way, if it is at constant pressure, we will write down this as Cp. If it is at constant volume, we will write this as Cv. But the formula remains the same. Accordingly, the heat measured will be at the constant pressure N delta T, or this will be the constant volume, whatever heat is absorbed to increase the temperature of 1 mole of the substance by 1 degree divided by number of moles and delta T. So looking at this, we can also write down the unit of the molar heat capacity, that is joule for heat, this per mole, then for temperature per Kelvin, or instead of that you can write down per Celsius also, joule per mole per Celsius, per degree Celsius. So based upon what is given in the question, it is basically the temperature difference only which we are talking about. Yeah, another important thing is, we wrote recently the similar formula for the specific heat capacity, where instead of this Cp we wrote as small cp, and instead of this number of moles we wrote it as m. So if we want to find a relation between the capital C and small c, what we will have is, we will write down like this: Cp, that is capital Cp, that is molar heat capacity, that is equal to molar mass multiplied by the specific heat capacity at the constant pressure. So this is molar heat capacity, that is Cp, capital Cp, that is equal to molecular mass multiplied by specific heat capacity, because this is for 1 gram. This is the heat required to raise the temperature of 1 gram by 1 degree, and this is for 1 mole. So A for 1 gram, it is Cp. For molecular mass, what it will be? Multiplied by, because this is for 1 mole, we are saying molar heat capacity. So obviously for 1 gram, if it is the specific heat capacity, for molecular mass it will be m multiplied by the Cp. So you have this relation for the Cp part. If we are writing for in terms of the volume, we will write down as the molar heat capacity measured at constant volume is equal to the molecular mass multiplied by specific heat at constant volume. So these formulas also you will require in some questions. There is one more relation which is important, that is molar heat capacity at constant pressure minus molar heat capacity at constant volume. This is equal to R, that is your universal gas constant. This is equal to R, right? So this is important relation. At times numericals can be asked. Okay, so suppose we ask a question like this: for oxygen molecule, calculate specific heat capacity at constant pressure minus specific heat capacity at constant volume. Right? This is to be calculated. For oxygen molecule. If we know this relation, we can calculate. Now what it is? You know that recently we have done, and I showed you the relation between capital Cp and small cp. What is the relation? Capital Cp is equal to molecular mass multiplied by that small cp minus, what was this? Molecular mass into Cv, that small cv. This is equal to R. right? So we can take this M common. Let's take M common here. M is common. M into Cp minus Cv is equal to R. What is the Cp minus Cv? Cp minus Cv is equal to R by molecular mass. So what is the molecular mass of oxygen molecule? It is R by 32. Okay, so this question can be asked like this also. Yes. Another thing, you have one more important relation. Molar heat capacity at constant pressure by molar heat capacity at constant volume. This ratio gives us gamma. Gamma is atomicity. Gamma is atomicity. It helps us in calculating the atomicity of a molecule. Okay. Like these Cp by Cv values, that is gamma which we are saying, for monoatomic gas, for diatomic, for a triatomic, the values are known. Monoatomic gas means all noble gases: helium, neon, argon, krypton. Diatomic, you can have say O2, N2, H2, Cl2, whatever. Triatomic, you can have say carbon dioxide, you can have H2S. Their values are known. For monoatomic gases, Cp by Cv value, this Cp by Cv value is 1.66. And for diatomic gas, it is equal to 1.40. For triatomic gas, it is 1.33. Okay, so you can just remember that gamma value decreases with the atomicity. More the atomicity, lesser is the gamma value, not the reverse. Now, to understand that, let's calculate one numerical. The question is, piece of aluminium metal which weighs 3 grams, it requires 5.4 joules of heat to increase temperature from 298 Kelvin to 300 Kelvin. You are asked to calculate heat capacity. You are asked to calculate the specific heat capacity and molar heat capacity. So what is heat capacity? Heat capacity is equal to Q by delta T. So what is Q here? 5.4 divided by the temperature difference, that is 2. So you will have 2.7 joule per Kelvin. That is heat capacity. For calculating specific heat capacity, you have the formula Q by M delta T. Right? What is Q? 5.4. The mass 3 gram. The difference 2. So when you solve this, it comes out to be 0.9 joule. So unit is per gram per Kelvin. This one, molar heat capacity Q by number of moles, N delta T. So for 3 grams, we'll find out what is the number of moles. Heat required 5.4. For number of moles, 3 gram. Given weight by molecular weight, the atomic weight of aluminium. The weight I wrote here, molecular weight there, that goes in the numerator, into 2, temperature difference. So you will solve this, 24.3 joule per mole per Kelvin. I hope this part is clear now. So moving on to the next question. Suppose it is given like it's required to raise the temperature of swimming pool from 20 to 25 degrees Celsius. We want to increase the temperature of swimming pool, water in the swimming pool, from 20 to 25. And that pool holds this much liter of water, 10 to the power 5 liters of water. How much energy is required to do so? If the specific heat capacity of water is 4.2 joule per Kelvin per mole, means they are asking us to calculate Q. We have the formula, specific heat capacity is equal to Q by M delta T. Right, you have to calculate Q. So Q is equal to C M delta T. You can put the values. C is given as 4.2. M we do not have m directly, but we have the volume. We have the volume, and that too in liters. So this, since it is given in CGS, we have to convert it into ml first. So to calculate the mass, we will have to use volume and density. So volume is this 10 to the power 5 multiplied by 10 to the power 3, this much ml, multiplied by density. Density of water is 1 gram per ml. So volume into density, this is giving you the mass of water, into the temperature difference, that is 5. Okay, so when you solve this, you will get it as 2.092 into 10 to the power 9. This much joule is the heat required. Yeah, moving on to the next question. It says, specific heat capacity of gas is this. This is small cv. Specific heat capacity of gas at constant volume is 0.313 joule. Constant volume. Molar mass of the gas is 40 gram per mole. Calculate the atomicity of the gas. Right. You know one relation for finding gamma. We should be knowing Cp by Cv. That is molar heat capacity at constant pressure by molar heat capacity at constant volume. Using this Cv, specific heat capacity, we can calculate molar heat capacity at constant volume. That is equal to molar mass multiplied by this Cv. That is equal to 0.313 multiplied by 40. You will multiply this first, calculate what is Cv. Cv comes out to be 12.52 joule per mole. Now next problem left over with us is to calculate this Cp. So Cp minus Cv is equal to R. We have to use this formula to calculate Cp. So what is Cp equal to? Cp is equal to Cv plus R. Right? You can put the value 12.52 plus. Now which R value to use? This is in joule. So we'll have to use R value also in joule. That is 8.314. That value we have to use. So when you add up this, you will get it as 20.834. Right. So this is Cp now. This is Cv. This ratio you have to calculate. Put this value of Cp here. Put this value of Cv here. When you calculate this, comes out to be 1.66. So 1.66 value, when we are taking, that 1.66 value is for what? Monoatomic gas. So you will write down it is for monoatomic gas. Followed. Please practice, children, whatever numericals we have discussed in this video and the previous sessions also. Okay. Thank you for watching.